Okay, take two. So I want to start today just with a couple of quick announcements. So the first announcement is at some point I said that G mod ZG abelian implies G is abelian. So this was in, I say this is an exercise at the end of the lecture when we were proving that any group of order P squared is abelian. So in the correct statement, is this was supposed to be cyclic. So the counterexample for abelian was given immediately beforehand in that lecture, or not quite, but discussed it, is the quaternion group. So if you look at the quaternion group, well, the center of the quaternion group is plus or minus 1, and the quotient is the Klein 4 group z mod 2 times z mod 2, which is certainly abelian, but the quaternion group is not abelian. So sorry about that. I corrected it in the notes that are on the website, but I just wanted to point that out in case lest anyone guard that statement in their head. Okay, that's one. Second announcement is I fixed something on the homework assignment. So in problem 2, n is not supposed to be 6. So problem 2 is the one about all automorphisms of Sn being inner. So that means all automorphisms of Sn are given by conjugation. Anyway, take n not equal to 6. So apologies if anyone got lost there. And then let me add one. So Rebecca pointed out to me that sort of the Cauchy's theorem problem on the homework. Well, there's an easier slash better way to deduce Cauchy from the Sylow theorem. Than the way I suggest on this problem. So yeah, no one's perfect. So me least of all. So anyway, thanks to Rebecca for pointing that out. You might think about that anyway. Of course, feel free to write up sort of whatever solution you want on that one. Particularly if you find sort of this better solution, don't feel like you have to use my sort of shoehorned solution. Okay, good. The first part of that problem is sort of independently interesting for other reasons, but there's a little bit of a shoehorn to sort of put Cauchy's theorem with it. So I apologize for that. Okay, that's all I wanted to announce. So I want to start class today with a little bit of a warm-up exercise. So I'll give you the exercise, and then say I'll give you probably about 5 minutes to work on it individually, and then I'll put you into breakout rooms for about 5 minutes to discuss it. And so if you finish it completely, either individually or in breakout rooms, then think about how you can generalize this. Okay, so the warm-up exercise is show the only group of order 15 is Z mod 15Z. Okay, so yeah, so I'll give you 5 minutes. I'll just keep everyone in this room right now, and then after that, I'll put you into breakout rooms to discuss with each other. Okay, so any ideas? Okay, let's hear it. Yeah, good. So I wrote out that computation here just so everyone can see it. Why is it abelian? Why is it? So where do you get the abelianness from that? Right. But but yeah, I think you need some argument to see that the elements in the two different groups commute with each other and the two different subgroups. So what you've said so far is sort of you have z mod 3z and z mod 5z inside. But then you need to say something to say to see that these commute with each other. But this is okay. But this is a good. I mean, this is a good start. And then there's just last step to fill in, so we can actually fill that in a second. Did anyone have another way to see it? Sorry, so yeah, I'm having a little bit of trouble hearing you. Or maybe if you can get any closer to the microphone, or raise microphone volume. Sorry. Yes, I do. Thank you. Uh-huh. And I think this argument is still missing something to show. And you still need to say something to show that things commute. Okay, good. So good. So this is a great way. So yeah, great. That's a great justification. Okay, thank you guys. So let's say that. So if you take any of these, so let's let H, so G be the group, then H a normal subgroup of size 15. Good, and then so H is the group, and then of size 5. H is the normal subgroup of size 5. Then G mod H has size 3, so G mod H is isomorphic to Z mod 3Z. And so sort of by this criterion I gave at the start. But so we don't know that H is the center. Sorry. Well, I think I misunderstood. What did you just say, Michael? Yes, H and K are normal. Okay. I see. So okay. This I'm sorry. I misunderstood what you were saying before. So I think this is okay. So yeah. Okay. I think so. I misunderstood what everyone was saying. This is a great way to do it. Thank you both. So we have G mod H intersect K is isomorphic to G mod H times G mod K. So this is what you want to use, right? Okay. Sorry, tell me which one okay. So HK is equal to G. Yes, okay, great. K mod. Okay. Yeah, so equals. Okay. Wait, sorry, then you apply which criteria? I see, but the quotient, but it has to be the center. Yeah, it has to be the center here. Okay, so we run the same problem. Okay, so well. Okay, so this is one way to do it. Okay, good. Okay, well, so anyway, this is one way to do it. Let me say two other ways to do it, though, that might sort of just be helpful, and one of them is sort of more helpful. Okay, so and this is sort of another one of these isomorphism theorems, so I can't remember which one. Does anyone, is this an isomorphism theorem? Does anyone know? I mean, I feel like this showed up on your homework, maybe, this statement. Okay, good. So yeah, so let me complete this solution first. So in H intersect K just has to be trivial by sort of order considerations. And then each of these is cyclic by order considerations, all by just order. Okay, good. So that's one good way to do it. Here's another way to do it. So fact that's useful to know anyway. If G is a finite group, with a unique, so this one down here, we'll call it solution 1. This will be solution 2. So if G is a finite group with a unique subgroup of any divisor of order D for any divisor D of the order of your group, then G is cyclic. So there's a very short proof by induction of this statement. So if you induct on the order of G, you can prove the statement. Yeah, good. So this is and so you could sort of invoke this fact. So solution 2 is invoke this fact. Because in this case, sort of, well, n3 is equal to 1. That's all. So there's one subgroup of order 3, and 5 is equal to 1. There's one subgroup of order 5, and so then there's one subgroup of order 15, the whole thing, and one subgroup of order 1, the trivial subgroup. So you can invoke this fact. It's another way. And then let me give a third solution, which I mean is sort of is maybe like this third solution is maybe the most systematic solution in the sense that I'm not sort of coming up with anything clever to invoke. I'm just sort of, if this is the solution you sort of would get at if you sort of just hacked away at this problem systematically, which is okay. So in we have, let me take H contained in G of order 5. So let me take this normal subgroup, this unique normal subgroup of order 5, the unique Sylow 5 subgroup. And well, I also have G, let me call it M. I have, well, it doesn't even matter that it's normal for what I'm about to say. So let me just take this subgroup of order 3. And I know sort of MH is equal to G just by order considerations. So I just need, so as we were saying before, so need to show elements of M commute with elements of G. Okay, but I mean, to see that, and I can look at the action of M on the subgroup H by conjugation. So M acts on H by conjugation. And so you get a map from M to the automorphisms of H, the group automorphisms of H. And this is a map of groups. So there's a group homomorphism from M to the sort of automorphisms of H, just by conjugation. But M is isomorphic to Z mod 3Z. And well, H is just Z mod 5Z. And the automorphisms of Z mod of the group Z mod 5Z, the cyclic group, well, they're all just given by multiplication by a sort of a unit in Z mod 5Z. So that's easy to check. And then, but in that group of units, you can just compute, for example, is isomorphic to Z mod 4Z. So I get a map. So this conjugation action gives me a map from Z mod 3Z to Z mod 4Z. So the image is trivial. So the kernel of this map is Z mod 3Z. Because if the image isn't trivial, then you'd have sort of some element of order 3 in Z mod 4Z. Okay, but that exactly says, so M commutes. So elements of M commute with elements of G. Or elements of M commute with elements of H. Because that's what aim. If the conjugation action is trivial, that means you commute with everything sort of in H. And so since this is sort of, this is a nice kind of argument. And we're going to talk about this kind of setup more on Thursday, I guess, when we talk about semi-direct products. Okay, so we'll come back to this kind of argument, but this is somehow a very powerful way to reason about the structure of this group by sort of, once you have a normal subgroup, so the setting of semi-direct products is where you have sort of a normal subgroup and then some other subgroup so that together generate the group. Then in that case, you can always sort of completely describe the group just by looking at this conjugation action. And in this case, sort of because the only possibility for the conjugation action is trivial, sort of we're done. Okay, good. So yeah, great. Oh yeah, I mean, maybe I should say, so someone else asked about this problem on the homework assignment. Someone asked about this problem on the homework assignment where you're constructing sort of a subgroup of index 3 in a non-abelian group where 3 is the smallest divisor of the group, or in 3 or sort of any n larger than 2. And this kind of procedure is one way you can do that, by the way. So if anyone else is sort of having trouble with that problem, you can sort of do something like this to sort of make a group of order 21 that's non-abelian. And the difference being that if you look at Z mod 7Z cross, well, now Z mod 7Z cross is Z mod 6Z, and you can give it sort of non-trivial map from Z mod 3Z to Z mod 6Z. And so this is sort of why that's possible for n equals 21. If you want, so in terms of, and I mentioned you could think about how to generalize this exercise. I mean, you might think about like, for what primes P and Q is it true that the only group of order PQ is sort of the cyclic group, Z mod PQZ? And certainly like this argument down here at least generalizes. Right. Okay, so good. So that's the warm-up exercise. So now back to the regularly scheduled programming. So We need to finish the proof of Sylow's theorem. So let me recall. So last time we showed existence. So we showed that if G is a group of, so G is a finite group. Of order G equals or P to the A times K, where P doesn't divide K. So if you sort of look at the largest power of P dividing the order of G, then there exists a subgroup of G of order P to the A. So that's what we showed last time. Okay, and so we did it by this inductive argument, right? Well, it's true for d mod pz, so trivially, and so then we were able to induce on the order of G, and we used that sort of either you could either use the center of the group to sort of go down to a smaller group. Like if the center was non-trivial, you could use that to get down to a group of smaller order, or if the if the center was trivial, then you could use the class equation to deduce that like the centralizer of some element was a smaller group where you could sort of take a Sylow subgroup. So that was the idea here. So now that we have the existence, we can sort of finish the rest of the Sylow theorems. So what we have left to show well, we need that the number of Sylow P subgroups divides the order of G and is congruent to 1 mod P. So the second condition combined with the first condition says it sort of divides the prime to P part of the order of G. So this and any P subgroup so any P subgroup is contained in a Sylow P subgroup. Whoops, and I have left one thing out. And finally, all Sylow P subgroups are conjugate. Okay, and so let's do this. And actually, in the way the argument is structured, we basically prove all of these statements together. So there's a close relationship between these three statements. So let's go. Proof. Okay. So I'm going to start. So G is a finite group. So again, write G is equal to P to the A times K, although probably won't need this as above. So P does not divide K. Okay, and so let me fix a Sylow P subgroup P sub 0 in G. So by existence, so since we've already proved that there is at least one of them, we can sort of just choose one of those. Okay, and then I'm going to let X be the orbit of P0 under P naught under the conjugation action of G. Okay, so the proof is going to go by sort of studying the action of subgroups of P subgroups of G on X. So we will just mark so proof of all three of these statements is by studying the action of P subgroups on X. Okay, so and the basic thing we're going to need is some, and we're going to need to understand something about the stabilizers. Oh, sorry, I see I missed something in the chat. Okay, so right, and we're gonna have to understand something about the stabilizers for this action. So that means we're gonna understand something about the normalizers of a Sylow P subgroup. And here's the main thing we need. Let's see. So if P is a Sylow, so this is not P naught, so this is any Sylow P subgroup of G, and Q is just a P subgroup. So recall, a P subgroup is just a subgroup of sort of order a power of P, but not necessarily like the largest possible power of P. Well, then the normalizer let me say it two ways. The normalizer in G of P of the normalizer of your Sylow P subgroup. So the stabilizer of the conjugation action of the whole group. If I intersect that with Q, that's equal to P intersect Q. So anything that's in the normalizer of P and Q is actually already in P. It is actually already in Q. Let me just rewrite this, and this is the same as the normalizer in Q of P. So, and this is sort of a slight abuse of notation. Let me maybe not write it like that. So this is the stabilizer of P for the conjugation action of Q on sort of Sylow P subgroups of G. So in the point, and when you have a group action, so like G acts on sort of the set of Sylow P subgroups by conjugation, but so does any, like, then any subgroup of G also acts. And so like, and the point of this is and the point of this lemma is that this quantity here, this normalizer in G of P intersect Q, this is the stabilizer of P for the conjugation action of the subgroup Q. And so we're sort of describing that stabilizer by saying it's just P intersect Q. So we're saying something non-trivial about it. So proof, well, let me write H for this thing we're trying to study. So H is a normalizer in G of P intersect Q. Well, definitely H contains P intersect Q because P is contained in its own normalizer. So good, so that's sort of one step. But on the other hand, we have that H times P is a subgroup of G. So this is something we talked about, and there was this day where we sort of just did a bunch of different things about normal subgroups and sort of the Sachs limit. So this is something we sort of talked about that day. Whenever you have sort of a subgroup P and then, so we have the subgroup P, and then we have sort of something inside of its normalizer. So this H is living inside of the normalizer of P. Then H times P is a subgroup. And moreover, the order of H times P, well, it's equal to the order of yeah, so this is equal to the order of P times the order of H cap H intersect P. So this is sort of something else that came out of the statement. So, and this is basically the second isomorphism theorem, I think. If I remember these numbers I told you not to remember, then I think this is the second isomorphism theorem. Okay, and so, but on the other hand, like, so the order of H is the power of P, and so the order of H let me say this is the power of P. Sorry, this is not right. Let me try this one more time. It's supposed to be the index. So this is the index of H. So it's the index of H intersect P and H times the order of P. Okay. Then the point in the second isomorphism theorem is that sort of HP mod P is isomorphic to H mod H intersect P. So that's sort of where this order is coming from. Okay, but this is divisible by P. By the number P. I have a lot of P's going on. Sorry about that. This is divisible by the prime number P because H is contained in Q. And Q is a P group. So H is by definition the intersection of the normalizer of P and Q. So that means this has to be this has to be equal to 1 because because P is a Sylow P group. So that means sort of P is already a P subgroup of maximal possible order, and HP sort of by this computation is all. Or sorry, not. I said yeah. I keep on saying not quite what I mean to say. This isn't just divisible by P. This is as a power of P. Because it's a subgroup of a P group. So any subgroup of a P group has the index of any subgroup of a P group is a power of P. This is a power of P. This is a power of P. But this is sort of already the largest possible, like this, what the order of this group is already the largest possible power of P that can be the order of a subgroup of G. So that means sort of this is 1. And so HP is equal to P. Well, actually, let me say it this way. So H intersect P is equal to H. Okay, but that means, so H is contained in P, but that means, so H is contained in sort of P intersect Q. We already had H is contained in Q. So that's the other containment we needed. Okay, so yeah, sorry, I probably that presentation wasn't as clear as possible. But the point is, you're using the fact that you if you had something else in the normalizer, sort of you'd be able to use in the normalizer inside of Q, you'd be able to use that to produce a group of higher P power order, a subgroup of higher P power order. But sort of you've already started with something of sort of maximal possible P power order, because P is a Sylow P subgroup. Okay, so that's the main thing we're going to use. Let's use this. Okay, so we're going to prove first. Let's look at the setup and what we have to do. And we start with some Sylow P subgroup, this P naught, and then X is supposed to be the orbit of P naught. And so, and what we need is that, well, first we need sort of the X contains all of the Sylow P subgroups. That's this third statement, that they're all conjugate. So there's sort of a single orbit of them under conjugation. And then, so if we have that, then we just need to show that X, like the size of X is congruent to 1 mod P. And then we also have to show that sort of any P subgroup is contained here. But actually, so we're going to argue in the order. So first, we're going to show that the size of X is congruent to 1 mod P. Then we'll use the size of X is congruent to 1 mod P to prove these other two parts. That's how we're going to do this. Okay, so let's continue. So once we have this lemma, sort of step one is we're going to show size of X is congruent to 1 mod P. So recall in X is, right this way, so X is the conjugates of P, so it's of P naught. So let me just number these conjugates, or P0 through PR. So these are the conjugates of P naught. So obviously P naught is one of the conjugates of P naught, but then there are sort of other ones. Okay, and so let's look at the action of P naught by conjugation. So G acts by conjugation on this set, but in particular, the subgroup P naught itself acts by conjugation. Okay, and so what are the orbits? Well, okay. Well, let me take an orbit. There's sort of two types. Well, first, there's the orbit of P naught. And that's just P naught itself, because P naught is in the normalizer of P naught. Okay. Now, if I look at the orbit of any other Pi, I equal not 0. So this is not, so this is some other Sylow P subgroup. Then the size of the orbit is, well, it's just the index of P, the index of the stabilizer Pi in P naught. But the stabilizer Pi is just P naught intersect the normalizer in G of Pi, which is equal by the lemma to P naught intersect Pi, which is not equal to P naught. Just because and Pi is not equal to P naught. So these are two groups with the same order. If these are two subgroups of G with the same order, if their intersection contains P naught, then they're the same subgroup. So that means, but okay, so since the stabilizer is not P naught itself, its index is sort of a proper divisor of the order P naught. So it divides P to the K, and it's not equal to 1. Thus, it's divisible by P. Okay, and so that actually concludes step one. So what do I mean? Well, we are trying to show that this set X of conjugates of P naught had size congruent to 1 mod P. We see that has one orbit of size 1, and then every other orbit has size divisible by P. So if you add, like, you get the set is just the size of the set is just to add up the size of all the different orbits. And so you're adding a bunch of things divisible by P to 1. So what you get is sort of 1 mod P. Okay, so that's the argument. Okay. So now step 2. And let's, so now we're going to show any P subgroup Q is contained in a conjugate of P naught. But the conjugates of P naught are just the elements of this subgroup X, of this set X. Right, so that will finish proving these other two parts, and then sort of once you know all the Sylow P subgroup conjugate, the fact that sort of the size of X is 1 mod P will tell you that sort of the total number of Sylow subgroups is 1 mod P, and that it divides G. So I'll say that more in a second. Okay, so and how do we? And why will both these follow from this statement? So the statement is that what was the statement I wrote down? The statement I wrote down was any P subgroup Q is contained in a conjugate of P naught. Well, in particular, any Sylow P subgroup is a P subgroup, and it will be contained in a conjugate of P naught, which will mean sort of it's one of these. It's in this orbit X. Okay. Good, but so now we just look at the action of Q on X, and we say, well, if I look at the orbit of Pi, this has size again. So it's the exact same argument. This has size Q colon the order of Q contain the stabilizer, the order of Q to the stabilizer of Pi, which by the lemma, so the stabilizer Pi, again, this is just Q intersect the normalizer Pi, which is by the lemma Q intersect Pi. And so, which is equal to Q, if and only if Q is contained in Pi. Okay, but now I'm done because X, the order of X is sort of the sum, the order of the orbits. And this is supposed to be congruent to 1 mod P by the previous step, On the other hand, like if the stabilizer of each pi is proper, okay, so let me. The proper subgroup of Q. Then this is sort of, this would be divisible by P. So this would be equal to 0 mod P. So sorry, I was a little lazy in how I phrased this. But the point is, like, so we're in a dichotomy here. Like each orbit, like the orbit of Pi is either in either its size is divisible by P. So what we deduced is sort of, yeah, what we deduced is either the size is divisible by P of this orbit, or Q is contained in Pi. So that's what our argument showed. You sort of extract this. So the size of the, yeah. So, but since we know the total size of the set is congruent to 1 mod P, that means one of the orbits can't be divisible by P. Like one of the orbits can't have size divisible by P, which means Q is equal to Pi. Or Q is contained in Pi, which is what we're trying to show. This Pi is a conjugate of P naught. Okay, so, well, and yeah, I apologize that wasn't as clean as it could have been. But I think this is sort of close enough that you can probably go through it on your own now. And the key point, though, is just to use this action. Like you're just using these basic divisibility things, arguments, and the action of P subgroups on sort of the set of conjugates of a fixed Sylow P subgroup. That's sort of the heart of the proof. Okay, so let me, right. I think I basically said everything. I mean, the divisibility happens just once you know all of the Sylow P subgroups are conjugate. Well, then it's just a single orbit for the conjugacy action. So any orbit has order dividing G, and that was the last thing I didn't say. Let's take, yeah, sorry, well, that took longer than I meant. So let's do a 5-minute break. And then in the last 10 minutes, I'll say something about the simplicity of the alternating group. And then we'll pick up next time. So let's take a 5-minute break. So we'll come back with 10 minutes left, so 1:35. Okay, so we'll get started again. Sorry, just a word, in case this proof, and it'd be very reasonable if this was too fast of a presentation of this proof for you. So again, feel free, and it's worthwhile going back and sort of checking through it carefully on your own. It's also in the book, and essentially the same proof is in Dubbin and Foote, so you can look there. I mean, given that it's in the book, maybe a word about why I even bothered to do the proof in class when we have such limited time in class. And it's just like, it's not just a proof, like it's a really nice illustration of how you can use group actions, and these like group actions is like basic counting arguments in sort of a more sophisticated way to like deduce a really strong result. So sort of, and somehow it illustrates that this is a powerful technique, but you can be a little bit clever about how you use it. You can really get some real mileage out of it. So I think it illustrates that nicely. Okay, so the last thing I wanted to do today, which doesn't use the Sylow theorems at all, but is sort of again related to this idea of classifying groups and classifying finite groups. So far we've seen a single simple group. We saw that A5 was a simple group. So I want to say something about the proof of the following theorem. So AN is simple for N at least 5. Okay. So we definitely don't have time to go through this carefully, but let's give you the main idea of the proof and to reduce it to something that you can work out as an exercise. And again, the proof I'm giving here is essentially the same, probably exactly the same as the proof in the book. So you can take a look there as well for more details. Okay, so well, we're gonna do it by induction on n. Well, there are many different proofs of this, by the way. So, but I like this proof that the book suggests. Okay, so base case. Well, we have to start at n equals 5. And we did that the other day by counting conjugacy classes. So this is this idea that any normal subgroup is a union of conjugacy classes. So sort of in this case, you could just count how many elements were in each conjugacy class and see and then compare with Lagrange's theorem and see there was no way to sort of put together conjugacy classes to get something that whose order divided the order of the group. Using that always sort of the identity element has to be one of your conjugacy classes. Okay, so that was n equals 5. So now we're going to argue by induction. So an inductive step. We'll also assume n greater than or equal to 6 and a n minus 1 is simple. Okay, so let me illustrate why how you use induction on this. That's sort of the main thing to see, I guess. So let me define GI to be the stabilizer of I subgroup inside of AN. So just for AN acting on the set 1 through n. So an alternating group is just a subgroup of the symmetric group, and the symmetric group is just the automorphisms of this set 1 through n. So AN acts on this, and then I can just look at the stabilizer of the element I in here. I'm gonna call that GI. I mean, these subgroups, the action of AN is transitive. It's not so hard to see. So these subgroups are all conjugate to each other, all isomorphic. But moreover, I mean, so GI is sort of a subgroup of the stabilizer of the stabilizer in Sn of I, and it's actually, which is isomorphic to Sn minus 1. And if you think about it, like under this isomorphism, this is just isomorphic to AN minus 1. You can S. And the point is, like, the definition of an even permutation, like just being written as one way to think about an even permutation is just sort of anything that we've written as a product of an even number of transpositions, and sort of, well, that will hold here as much as here if you stabilize this other element, this sort of one element. So this is not, this part's not so hard to check. But so in particular, by the inductive hypothesis, we get that GI is simple. Okay. So how is this useful? Well, so to show AN is simple, we need to sort of start with a normal subgroup and then show that normal subgroup is either the trivial group or the whole group. So here's a sort of observation that's going to be helpful. AN is generated by these subgroups G1 through G2, or G1 through Gn. So that means any subgroup of AN that contains all of these GI is AN itself. Okay, and so let me just sketch y. Well, sort of if tau is contained in an, then sort of tau is equal to, so let me write it this way. Tau is, so if sigma is an an, and sigma is equal to tau 1 through tau 2n, 2m, so for tau I transpositions. So then I can just write this as tau 1, tau 2 times tau 3, tau 4, and so on, up to tau 2m minus 1 times tau 2m. And then so each tau I times tau I plus 1 is in gi for some I. Gj for some j. In y, well, so the reason I'm doubling up the transpositions is so I get elements of the alternating group. So a product of two transpositions in the alternating group, if I just sort of take one transposition that's not in the alternating group, that's just in the symmetric group. So the reason I'm doubling up is to get something in the alternating group. But then like a product of two transpositions can move around sort of at most 4 things. And then everything else has to be fixed by it. But I mean, since n is larger than 4, that means sort of each of these products fixes something and sort of fixes some number I. So it's in one of these stabilizers. Okay, so that's elementary. Good, and so then now let me state sort of the main tool you use to finish the proof. You show that if you have a normal subgroup of an, and it contains a non-zero sigma such that sigma of I is equal to I for some I, then H is in fact equal to an, so non-trivial sigma. So it contains some permutations, not the identity permutation, but fixes some element. So the proof of this. Well, sigma is contained in GI. So H intersect GI is a, so it's saying sigma I is equal to I, just saying you stabilize I. So that's saying you're in the subgroup GI. So H intersect GI is a normal subgroup of GI. That's not trivial because this element sigma is not trivial. Thus, it is equal to GI. Because GI is simple. So you went from having just this one element that fixed I to having every element that fixes I. So, okay. So this is really where you use the inductive step. We're using the fact that the, the inductive step we used to show that GI was simple. And then sort of we're using the simplicity of GI here to sort of get this mega upgrade to having all of GI. So this says H contains GI. But then, I mean, the GI are all conjugate. So the GJ are all conjugate. So H contains GJ for each J. Because H is normal. So if any normal subgroup, so if it contains one thing, it contains all its conjugates. So it also contains all these other GJ, and thus H is equal to G, because so H is equal to AN. because we already saw that AN was generated by these subgroups, GI. So sorry, I'm a couple minutes over. Let me just say, in the rest of the argument, like just give yourself a non-trivial element. And then sort of play around with conjugation. To get one that sort of, to get one fixing. Fixes something. So then you break it, like there are like basically two cases you have to consider. Sort of, you have to consider when there's a cycle of like 3 or more in your non-trivial element, or when it's sort of all 2 cycles. But this is sort of, and this is a good exercise to finish this out, or you can just look in dominant input to see the end of this proof. Apologies for going over. Let me end here.